Okay, forget all the scary equations for a second. What if I told you there's a single idea in math that can measure a jagged coastline, figure out the energy needed to launch a rocket, and describe how a whole system comes together from its tiniest parts? Well, that idea is the integral. And really, it's all about one thing: perfect accumulation. So how are we going to get our heads around this? Simple. Here's our game plan. We're going to start with the ancient problem that sparked this whole thing. Then we'll check out the integral's two-faced identity before we uncover the beautiful connection between them. We'll take a quick look at the integrator's toolkit, and then we'll see how this whole concept becomes a language for describing our world.
All right, let's jump right in with the core problem. I mean, this is the visual puzzle that calculus was literally invented to solve.
I mean, really think about it. Finding the area of a square or a triangle, that's easy, right? We've got formulas for that. But the real world is messy. It's full of curves. Think about coastlines, hills, the path a planet takes. How do you find the exact area under a curve that's changing all the time?
Well, the first brilliant idea wasn't to solve it perfectly, but just to get close enough. Imagine filling that curvy space with a bunch of tiny rectangular blocks, kind of like Legos. We know how to find the area of each rectangle, so we just add them all up. This method, it's called a Riemann sum, and it gives you a pretty darn good estimate.
But here's the thing. An approximation isn't perfection, is it? The real genius move is what comes next. What if we make those Lego blocks not just small, but infinitely thin? As they get narrower and narrower, all those jagged edges from our approximation just smooth out, and the error completely disappears. In that moment of infinite precision, the estimate becomes a perfect, exact measurement. That leap from close enough to absolutely perfect, that is the integral.
Okay, so now things get interesting. This one idea, the integral, it actually plays two very different but equally important roles. You could say it's got a bit of a split personality.
On one hand, you've got the definite integral. This is the direct answer to our area problem. It spits out a single concrete number, like the total area is exactly 40. Simple. But then, on the other hand, you've got the indefinite integral. Its result isn't a number at all, but a whole formula, or really a whole family of formulas. Think of it as giving you the general recipe, not just the final dish.
So we have these two different ideas. One gives you a number, the other gives you a formula. And for centuries, people thought of these as totally separate things. But the bridge connecting them, it turned out to be one of the most profound discoveries in the history of, well, anything.
First, we got to talk about this key idea, the antiderivative. You probably remember that a derivative tells you the rate of change of something at any given instant, like your car's speed at one exact moment. Well, the antiderivative does the exact opposite. It takes all that moment-to-moment speed information and pieces it all back together to reconstruct your entire journey.
And boom, here it is, the mind-blowing reveal. The fundamental theorem of calculus proves that these two ideas are deeply, fundamentally connected. It says that the super tedious process of adding up infinite rectangles to find an area is the exact same thing as finding the antiderivative, the reverse of a rate of change. Accumulation and rate of change are perfect inverses, just like addition and subtraction. This one idea is what unlocked modern physics and engineering. It's huge. So, knowing they're connected is awesome, but actually solving integrals can be tricky. So over the years, mathematicians have developed a whole set of really powerful techniques to get the job done.
One of the most common tools in the box is called U-Substitution. You can think of it like a clever disguise. You take a messy, complicated integral, and you find its trickiest part. You then temporarily replace that part with a nice, simple variable, we'll call it u, which makes the whole problem way easier to solve. Once you have that simple answer, you just take off the disguise to get your final result. Pretty neat, huh? And U-Substitution is just one tool in the workshop. Different problems need different tools. You might use integration by parts when you're dealing with two functions being multiplied. You'd grab your trig identities when you're working with waves and oscillations, and you'd use partial fractions to break a monster of a fraction down into simpler pieces you can actually solve. Each tool is specialized for a different kind of mathematical puzzle.
And now we get to the really wild part. Because integration isn't just about finding areas on a graph. It is the language we use to describe how things accumulate in the real, physical world, in any dimension. A line integral, for example, adds up some quantity along a one-dimensional path.
And this isn't just abstract, it's exactly how physicists calculate the total work you need to do to push something along a curved path when you're fighting a force like gravity or wind.
Then there's a surface integral, which sums up a quantity over a whole two-dimensional surface. This is absolutely essential for measuring what we call flux, things like the total amount of sunlight hitting a solar panel or the volume of water flowing through a dam. It's the bedrock of electromagnetism.
And you can probably guess the next one. A volume integral adds up a quantity throughout a three-dimensional space. This lets us find the total mass of an object that has a varying density, or the total electric charge that's just hanging out inside a cloud.
You know, this slide really brings it all home. The integral isn't just one concept, it's a whole way of thinking that we can look at through different lenses. Look at the table here. Mathematically, sure, it's about accumulation. Physically, it's the language of work and energy flow. Epistemically, which is a fancy word for how we know what we know, it's about that journey from a good guess to a perfect answer. And maybe most profoundly, on a philosophical level, it's the formal process of building a complete, seamless whole from its tiniest, infinite parts.
So the integral is way more than just a tool for a math class. It's a fundamental lens for looking at the world. It gives us the power to precisely measure the irregular, to track continuous change, and to understand how our complex reality is built from simple pieces. And that leaves us with one last big question. If integration is how we understand wholeness emerging from tiny parts, what other complex systems, from our economies to our ecosystems, are just waiting to be understood if only we could find the right way to sum their smallest pieces?